Okay, you know how to do empirical formula calculations now using those 4 steps that I showed you, and you know how to do molecular formula calculations using the molar mass and the empirical formula. What's left is a very specific type of empirical formula problem that's actually related to something that happens in organic chemistry all the time. When a new organic compound is synthesized, the empirical formula calculations are usually very difficult because it's hard to figure out how much hydrogen, how much oxygen, how much carbon is in the compound. So one of the things they do is they burn the compound. They burn a measured mass of the compound, and they capture the carbon dioxide and water vapor. Remember, burning organic compounds is combustion, and that results in carbon dioxide and water vapor. Looks like this. Now, the interesting thing about this and why this works so well is that all of the carbon, indicated here in red, in the organic compound ends up being in the carbon dioxide. And all of the hydrogen, indicated in the blue, ends up being part of water. And that's true whether or not you have just a hydrocarbon, which is carbon and hydrogen, or an oxo compound, which is carbon, hydrogen, and oxygen. Now, the oxygen is kind of all over the place. It's both comes in the reactants in the form of oxygen in the air, but sometimes there's already oxygen in the compound, and it ends up in both products. So it's a little more difficult to figure out how much oxygen, but it becomes easy if we can figure out the other two. Okay, so that's the important thing that goes along here, is that all of the carbon from the original compound is now in the carbon dioxide, and all of the hydrogen from the original compound is now in the water. So that means that if I can figure out, based on how much carbon dioxide I am able to capture, how much of that carbon dioxide is carbon, then I'll know how much carbon was in my original compound. And I can do the same thing with water to find the amount of hydrogen. And then by subtraction, I can find the amount of oxygen. And then I'll have the masses of all 3 elements in my compound, and I'll be able to do a regular empirical formula calculation. So let's do an example. You're going to need to write this example down so that you can follow along with the explanation of how I do it. So caproic acid is actually one of the compounds that's produced by animals, farmyard animals, specifically goats, and it gives them that very distinctive smell. If you ever smelled goats, you're smelling caproic acid primarily, among other things. Okay? It's an organic compound. It contains only carbon, hydrogen, and oxygen. We're going to combust 1 gram of this compound, exactly 1 gram, and we're going to capture the carbon dioxide and water vapor and weigh it. Okay, so we combust 1 gram, we produce 2.27 grams of carbon dioxide and 0.931 grams of water. Now, the molar mass of caproic acid can be measured with a mass spectrometer, and it's measured at 116.18 grams per mole. From that information, we're going to calculate the empirical and molecular formulas of caproic acid and then write a balanced chemical equation for its combustion. Okay, so that's our goal. Let's figure out how we're going to do it. To start with, we know we're working with CX, HY, and OZ. We know this thing has carbon, hydrogen, and oxygen because it says so. We know we're combusting it, which means we're always going to produce CO2 and H2O. And all of the carbon in this compound is now here in the carbon dioxide, and all of the hydrogen is now here in the water. So I need to figure out then, there are 2.27 grams of carbon dioxide. I need to figure out how much of that 2.27 grams is carbon. Well, if I do my percentage composition calculation for carbon, I know that there are 12.01 grams of carbon and 32.00 grams of oxygen in carbon dioxide. That's 44.01 grams of CO2, and that means that the percentage of carbon in CO2 is 12.01 over 44.01, which is 0.2729, or 27.29%. That means anytime I have carbon dioxide, a little more than 27% of the mass of the CO2, whatever mass that is going to be carbon. So I know then that of this 2.27 grams, a little over 27% of that is going to be carbon. So if I multiply the amount of carbon dioxide by the percentage of carbon, that's the percentage of carbon in any amount of CO2, I get 0.619 grams. That's the amount of carbon in the carbon dioxide, which is also the amount of carbon that was in my original compound. So 0.619 grams is the mass of carbon in that compound. I can do the same thing with the water. 0.931, that's a 0, 0.931 grams of water. Well, how much of water's mass is made up of hydrogen? I can do the same thing. For hydrogen, there's 2.02 grams of hydrogen and 16.00 grams of oxygen in 1 mole of water, or 18.02 grams of H2O. Okay? So the percentage of hydrogen then in water is 2.02 over 18.02, which is 11.2%, or 0.112. Okay, so the percentage of hydrogen in any amount of water is about 11.2%. So in this 0.931, if I multiply by the 11.2% in decimal, 0.112, I find that there are 0.104 grams of hydrogen in the water. All of that hydrogen came from my compound, which means the original compound contained that mass of hydrogen. So now I know the mass of carbon from my original compound and the mass of hydrogen. The only thing I need left is how much oxygen was in my original compound. But I can't do it this way because the oxygen is all over the place. Fortunately, what do I know? I know that I combusted exactly 1 gram of the compound. And if that 1 gram was made up of this much carbon and this much hydrogen, then the rest has to be oxygen. So I'm going to subtract 0.619 grams of carbon and the 0.104 grams of hydrogen from my 1 gram, and what's left is 0.277 grams of oxygen. Okay? So now I have the masses of all 3 elements in my compound, which is exactly what I need to do the empirical formula calculation. So let's do that. So I started with 0.619 grams of carbon and 0.104 grams of hydrogen and 0.277 grams of oxygen. That's step 1, the mass of each element. The step 2 was to convert each of those masses to moles. 1 mole of carbon is 12.01 grams. That gives me 0.0515 moles of carbon. 1 mole of hydrogen is 1.01 grams. That gives me 0.1030 moles of hydrogen. And 1 mole of oxygen is 16.00 grams. And that gives me 0.0173 moles of oxygen. That's step 2. Step 3 is to divide each of these by the smallest of the numbers. The smallest number of moles is 0.0173. So I divide 0.0515 by 0.0173. It comes out to be 2.97. Well, we're trying to get a whole number here, so that's 3 moles of carbon. 0.1030 divided by 0.0173 gives me 5.95, but that's 6 moles of H. If you're within 1/10 of a mole, you can round it. Otherwise, you have to multiply everything through by a common factor. And then finally, 0.0173 divided by 0.073 is 1 mole of oxygen. Okay, so my empirical formula then is C3H6O. That's my empirical formula, C3H6O. That's the first part. Okay, now the second part is I want the molecular formula. And if you remember the molecular formula, you need the empirical formula, which I now have, and you need the molar mass. So the empirical formula is C3H6O. The molar mass of C3H6O is 58.09 grams per mole. Okay? If my actual formula for caproic acid was C3H6O9, its molar mass would be 58.09. But the actual molar mass that was given in the compound, or in the problem rather, was 116.18. Now, you don't have to do the math out. I'm going to, but if you look at this, you should be able to see that 116.18 is twice that, right? But all I need to do then is divide the actual molar mass by the molar mass of the empirical formula, I get a whole number, 2, and that means that I multiply C3H6O times 2, everything doubles, C6H12O2, and that is my molecular formula. Okay? The last part was to draw a balanced equation for the combustion of caproic acid. So caproic acid is C6H12O2 plus O2 goes to CO2 and H2O. I'm going to let you balance this one on your own because you know how to balance. It's not a difficult one to balance. So you can do that one on your own. Okay? So most of the problems that are advanced are like this. Okay? And the combustion problems are certainly the most common. So go back, look it over again, work through the example, and you'll have some practice on this in class.